Okay, folks, today is mostly chemistry. Before we go in the next lecture into building polynomial approximations and intervals and such like, we need to discuss how chemists think about approximations. The reason we are doing this and the reason why approximate solutions are required is, as you come to realize in your second and third year, most equations that actually describe the physics of our problems, like Schrödinger's equations, are not soluble exactly. So even for a two-particle system, the wave function is six-dimensional, and that quickly becomes a problem as you go to bigger and bigger systems. And so there's a notion in physics and engineering of good enough. So how can we find a representation of the same problem with simpler equations, simpler models, and so on, that's actually analytically or numerically soluble, that is approximate, but provides us to the answer, to the accuracy that we actually practically need. Concentrations maybe 3 decimal places, for probabilities maybe even 1 decimal place. So we don't require absolute accuracy, and so you can often substitute real difficult problems that are exact by much simpler problems which are approximate, and today is a kind of a philosophical introduction into how chemists think about approximations. So let us start with chemical kinetics, or physical kinetics in this case. So let's say there comes a point in the life of every Russian where you just need a little bit of plutonium-239. And so the way you do it is you put a slab of uranium-238 in the path of some neutron beam. And that will usually come out to a working reactor. And what happens is uranium absorbs a neutron, 239 uranium, and we will assume that we just gave it a burst of neutrons and we instantaneously converted some uranium into uranium-239, but then it will decay. What happens is the neutrons inside this nucleus become unstable with respect to what's called a beta-electron decay, and they emit an electron and an antineutrino, and they become protons. And so what will happen is this will go one way forward in the periodic table, and then become neptunium. 2, 3, 9. Neptunium, and that happens on the time scale, so the reaction rate constant in this case is 2.55 per hour, hours minus 1. And then neptunium also decays fairly quickly with the rate constant that is a bit slower, but not by much. 2.0177 per hour into plutonium. And that's quite stable, 27,000 years is the half-life, and so what we will focus on is actually this part. So we assume that we obtained some uranium-239 out of this neutron burst, and then we would like to consider 2 sequential reactions that convert it into plutonium, and then we can assume that on the time scale of our experiment, which would be in the hours 2 days, 27,000 years is not a sufficiently rapid process to be taken into account. What we will have to do is do exactly the same as what we have done for reactors and then Rallis and Foxes in the previous lecture, is we have to ask ourselves what's the uranium by dt. So the quantity or concentration of uranium by dt is going to, well, it is decaying with the rate constant K1, so there's a minus because the concentration is reduced, then K1, and then the concentration of uranium itself. The more there is, the more is consumed per unit time in the reactor. And that's basically it. Well, insofar as we are concerned, there's some initial condition, initial concentration of it, and there's only one process that is draining our uranium. In the case of neptunium, there are 2 processes. One is adding to it, the other is subtracting from it. So d neptunium by dt is going to be plus K1 U. So the more uranium there is, the more decays per unit time into neptunium, hence the plus, and the concentration of uranium here. And then the decay of neptunium itself subtracts from the current concentration, so minus K2. And the more neptunium there is, the more gets removed per unit time. So radioactive decay is also a constant fraction per unit time. And then eventually it arrives into plutonium, dPu dt. And there's just the process that replenishes it, and we neglect the subsequent radioactive decay because it is very slow. So plus K2, and the more neptunium there is, the more arrives into plutonium per unit time. So these are our kinetic equations, and as you've seen yesterday, what was it, Thursday, Wednesday, that this is rather hard to solve. If we plotted, if we ask a computer to solve it and plot a graph, so we will have the quantities of these substances against time, you will see that the concentration of uranium just simply goes down, right, exponentially, with on the time scale of just under an hour. So if we put our time scale here to approximately 20 hours, and that's 10 hours, that is a few clicks per hour, so the concentration of uranium will decay very rapidly. So if that was V0, that will go like that. And disappear. At the same time, what happens is it gets converted into neptunium, and that neptunium gets converted into plutonium. So at the same rate as uranium had disappeared, we will have neptunium accumulating like that. But then what happens to neptunium? Of course, it decays into plutonium, and it decays to plutonium considerably slower than uranium got into neptunium. Note that the rate constant is slower, so then this yellow curve continues, but not nearly as rapidly as the blue curve decayed. It has a decay stage. And then, of course, what is going to happen is this yellow curve, which is neptunium, gets converted into plutonium, of which originally there was none, but as neptunium decays, it will accumulate. Something like that. It will grow at roughly the same rate as the yellow curve is decaying. Okay, so that's our neptunium, that's our plutonium, and that's our uranium. This is something that you would often see, and in this particular case, no approximations are actually possible because everything that takes place in the system takes place at roughly the same scale of time. So one is a few events per hour, the other is a few events per day, but we are dealing here with the processes that happen on roughly the same time scale. Now, what is going to happen if we have processes that actually happen on very different time scales? So let me draw you another decay chain where the second process, so this second stage, is massively faster than the first. And then let us analyze what is going to happen under those circumstances. So there's another little fragment in the radiochemistry of thorium, where 2, 3, 4 thorium goes into 2, 3, 4 actinium, and that eventually goes into 2, 3, 4 uranium. Again, a sequence of beta electron decays that just pushes, this is an alpha decay, a thing that pushes the system down the periodic table. So what we have here is that this K1 is rather slow. K1 is 0.00173 per hour. I think in the chemical kinetics we will usually have it per second, but it's per hour. However, this process is significantly faster. K2 is 2 orders of magnitude faster, 0.149 per hour. The second process is 100 times faster than the first. we can write down exactly the same equations of motion. In fact, they would be identical to the equations of motion that we have here, except that would be thorium, that would be protactinium, and that would be uranium. And then we can solve them and take a good look at what comes out. So in this second case, again, this is quantity or concentration as a function of time that is measured in hours, and actually no, in this case days, because the first process is so slow. Thorium is simply going to decay on the time scale of days. So this will be a slow exponential decay. So that is thorium, that's the initial concentration, and the time scale here is approximately 100 days. 50, 25, 75. When it moves to protactinium, notice that the reaction that replenishes protactinium, that arrives into it, is very slow. However, the reaction that depletes it is very fast, which means that the instant something arrives, it is consumed. There will never be a large steady state concentration of protactinium in the system. So it will blip up a little bit, and because it's consumed so rapidly, the concentration will pretty much stay constant until it eventually decays as well. So this is our protactinium. However, this rapid process would then replenish uranium-234, which again has a half-life in the thousands of years, that we don't need to worry about the subsequent decay processes. And so if we draw uranium, what happens is thorium jumps into protactinium, which then instantly jumps into uranium. And so uranium accumulation is actually going to be at roughly the same time scale as thorium depletion. And eventually, the whole thing will get converted into uranium-234. There's something rather special here. Notice what happens to protactinium. The concentration blips up, but then stays roughly constant with very low rate of change. So neither does this get particularly fast, nor does this get particularly large. For all intents and purposes, in this case, d-protactinium by dt, most of the time in this reaction, except for the very first little moment, is 0. This is called a steady state approximation. Or the other word is quasi-stationary. And the word quasi-stationary simply means that the concentration is approximately stationary throughout the chemical process. Let us now think about what this is going to do to our equations of motion. So let us rewrite this system specifically for the second case, and then use that approximation to see what's going to happen. So our d thorium by dt is minus K1 thorium, d protactinium by dt is plus K1 thorium minus K2 protactinium. I'm just literally copying the thing. And then d uranium by dt is plus K2 protactinium. If we now put that protactinium derivative to 0, so that is now our approximation, notice that it takes what was previously a differential equation, and therefore rather hard to solve, and makes it into an algebraic equation, which is trivially easy to solve. And in fact, this algebraic equation would allow us to eliminate protactinium completely from consideration. So let us rewrite this algebraic equation and see what that means. K1 thorium is, and I'll move that over to the right hand side, K2 protactinium. Protactinium we really don't like. It's the intermediate stage. It's not present here. It is present here. Why don't we eliminate this one here? So we can say that protactinium concentration is actually K1 over K2, the concentration of thorium. If we plug that back into the system of equations, one of the two equations gets eliminated. So what we now have is d thorium 5 dt is minus K1 thorium, something we actually already know how to solve. The second equation disappears, and in the third equation K2 gets cancelled out, and we've got K1 thorium. So d uranium 5 dt is plus K1 thorium. Notice that protactinium is gone. We can now actually solve this quite easily in the same way as we solved it on that table. The first equation and the second equation are actually almost independent. At least the first equation doesn't depend on the second one. And this is standard radioactive decay, for which we know the solution. So that thorium at time t is thorium at time 0 E minus K1T. Right? We solved such equations several times in the previous lecture. And then since we know this, we can substitute it back there. And therefore, d uranium by dt is, what is it? K1 thorium 0 E minus K1T. But that's also trivially soluble because we can simply just integrate both sides. Put an integral here and an integral there. Moving dt over here. We will have an integral du, which is basically just du plus a constant, equal to the integral of that, where once we integrate the K1 will disappear, so we will have thorium 0 E minus K1T plus a constant and with a minus sign here. Since we have two constants, they are fundamentally just one constant, and uranium concentration is a function of time. And then this constant is determined from the fact that initially there was no uranium in the system, so at time 0, this exponential becomes 1. That has to be exactly subtracted out by this to get a 0, and so C is actually thorium not. So after we substitute the facts, we use uranium at 0 is 0. We get uranium at T is thorium not 1 minus E minus K1T. And these are approximate solutions. So that is the first, or that's the second equation, and that one is the first one. And then, of course, if we want to actually find out what the concentration of protactinium had been, we just use the expression here, because it's related to the concentration of thorium. So our PA of T is K1 over K2 times thorium. So that. Minus K1T. And that is our third equation. So what happened is originally we were faced with a really difficult triple coupled system of differential equations, which at the moment we don't know how to solve. And if I were to actually go and solve this rigorously on the board, that would have been a whole hour. And the results would be tremendously large, and we'd rather not. Then we noted that there are cases where this quasi-stationary approximation applies. We did a bit of philosophy, and that simplified the system to a point where our current knowledge of differential equations actually allowed us to solve this. Now, what is very important is that there's a condition attached to this, that the second reaction is much faster than the first, and so this only applies if K2 is much greater than K1. And if we were to plot these approximate solutions, I've actually done it in your handout, directly on top of the exact solutions, you would notice that for all intents and purposes, they are coincident with a tiny difference. So white is the approximation. The only difference that would be seen is here. That in the first instance where this steady state approximation does not yet apply, the behavior of the approximation doesn't match the behavior of the big system. But for all other cases, it would actually be extremely good, to the extent that if you look at your handout, it's actually rather hard to tell the difference between those curves. They're almost on top of one another. So that is an example of an approximation. We stare at the system long enough, we realize it is hard to solve, and we'd rather not do it, and then we make a sensible assumption about it. That assumption is casted to an algebraic form. That algebraic form includes some simplifications. The simplified system is easier to solve. Another good example of the same, actually, that the Nobel Prize was awarded for back in, I think it was the 60s or the 70s, is density functional theory in quantum mechanics, where this giant hyperdimensional object called wave function has been replaced by three-dimensional electron density, which is much easier to solve for, without, for quite a few systems in chemistry, even it being too much of an approximation. And so we are using that method whenever we are doing computation on chemical systems these days. So some things are much easier to solve than others. This is one example. Another example of frequent occurs in chemistry, and this goes back to quantum mechanics, is that interatomic forces tend to be what computer scientists call expensive. That is, if we have two atoms interacting, then the task of calculating the force between those two atoms is computationally, well, protracted and requires a large computer. So let's say exact energy of a two-atomic system as a function of the distance between the two atoms. So exact is expensive. In a pretty literal sense, it would be rather, tough to find or buy a computer that would be able to do it. But we can then, fudge it and say, okay, well, it's a bond, right? Why don't we treat it as a ball on a spring? After all, we do know that bonds vibrate, and so to some extent they do behave like two balls on a spring. And then, of course, the spring has a force constant, and as you remember from your Hooke's law from just elementary school, the energy of this arrangement, the potential energy of it, was Kx minus x naught squared over 2, where x naught is the equilibrium length of that spring. X. Why don't we do the same? So we say, okay, assuming that the bonds behave as balls on springs, e to the r will be approximately equal to some force constant divided by 2, r minus equilibrium squared, where our equilibrium is the equilibrium length of the bond at which the energy is minimal. And we all know how to solve such things. Okay, let us think about what this would practically mean. This is used in molecular dynamics, quite a lot of modeling, including in our own chemistry department. You can these days take an entire virus, atom by atom, put it into virtual reality and run a couple of microseconds of real physical time. And obviously that's not quantum mechanics, this is these approximations. And in fact this exact approximation, it's called harmonic approximation, is used in quite a few cases. Let us plot it relative to what we know is the ground truth, and let's analyze how it is. And also what it can and cannot do. And in the next lecture, we will actually be busy building these polynomial approximations to real functions. Okay, so that's our energy. And that is our interatomic distance. Let us first plot roughly the ground truth, what we know to be the case. Well, we know that when the two atoms are separated by a very large distance, the interaction energy between them is zero. They do not interact. And then, if it's, I don't know, fluorine and hydrogen, you bring them together, the energy is dropping because the energy of that arrangement is lower than the energy of when they are far apart. So when the bond is formed, some energy is released, and therefore the energy of the system drops. Behave like this. But then at some point, of course, we reach the real actual bond distance, where the energy is at a minimum. And at some point, we will start pushing the atoms into each other, and they don't really like it because of inter-electron and internuclear repulsion. So at some point, the energy will start growing again, and in fact, as we are pushing nuclei into each other on the chemical time scale and energy scale, the energy effectively becomes infinite. And so sooner or later, we have a charge collision, and so there's an asymptotic jump into infinity in here, a very typical singularity. And that is our equilibrium. And this is how the energy must behave. Let us now think about how this thing behaves. And clearly at our equilibrium this energy is zero, and so I will shift it a little bit down the scale so it matches with our curve in here. We have effectively a quadratic curve there, so what it will look like is this. So this is true, and that is harmonic. Well, around the equilibrium bond distance, if we are not pushing that molecule too much, if it's sitting at some low temperature and not doing any chemistry, well, it's all right. So when we are between here and here, it's a pretty decent approximation. We match that quadratic to the curve neatly, and I will tell you how to do it in the next lecture. It's pretty serviceable. What, however, happens at larger distances is profoundly unphysical, because it's actually impossible to break such a bond. Right? When we pull the two atoms apart, energy would go to zero, sooner or later the bond will break. However, under the harmonic approximation, the energy would not go to zero, it would instead go to infinity. Right? So, harmonic potentials in molecular dynamics do not permit the bonds to be broken. Right? So, this breaks chemistry. Which is actually okay in situations where no chemistry is involved. For example, non-covalent van der Waals complexes between proteins. When the two proteins come together, as a result of some regulatory cascade inside the cell, they're not covalently bonded. They are bonded by a mixture of electrostatic van der Waals and various polarization interactions. And so, something like that might be perfectly serviceable, but you can see it's not accounting for the fact that chemical bonds can be broken. The other thing that happens is, even though the true potential must go to infinity, the quadratic potential, of course, would not. So perhaps I should redraw this red line differently, in that the white line actually goes considerably faster than the red line here. So it will look something like this. At zero separation, the quadratic curve does not go to infinity. So this energy here is finite, which practically means that atoms can go straight through one another. So push them into each other and then it will come out on the other side. So clearly this breaks vibrational spectroscopy, right? So non-physical. And so this approximation, even though it is used extensively across physical and chemical sciences, including for systems that are not atomic, for example, vibration of engineering structures is often assumed to be harmonic, vibrations of crystals, so phonons inside them, is assumed to be harmonic. Its range of validity is fairly narrow, so long as you are not doing horrible things to the system, it will be fine. Okay, but of course people are clever and they decided to, well, say, this is really quite horrible, right? Why don't we get ourselves a better approximation? So this was harmonic. The next best thing that quantum chemistry people, more specifically molecular dynamics people, came up with is called Morse potential. They say, oh well, that sort of doesn't really work. In certain cases, why don't we use the following? E equals E equilibrium. This is equilibrium energy here. It's called E equilibrium. And 1 minus E minus A R minus R equilibrium. And then all of them squared minus E equilibrium. If you ask where this comes from, nowhere in particular. It comes from people's imaginations. It comes from them trying to fit a simple functional form to what they know to be true. And if we draw the same plot again with the Morse potential on top of it, our ground truth is this. And the Morse potential, if we draw it, is going to look like this. It actually correctly behaves at infinity and then matches the system pretty well, but then goes to a finite energy instead of infinity. So that is Morse, and that is truth, which is very, very hard to compute. Okay, so the Morse potential has fixed our bond breakage problem. When we try and pull the two atoms apart, the energy would correctly go into zero. However, when we try pushing the atoms closer together, so it is now incorrect. If we try pushing the atoms close together, the situation with the zero separation still corresponds to finite energy, which is non-physical. So that is still broken. And so even smarter chaps came around and said, well, not only must it go to zero at zero separation when the two nuclei collide, must go to infinity, but actually when the electrons begin colliding. So not only has this to go sharply up at zero, it has to go sharply up considerably earlier than that, because, well, it allows a covalent ray. That as you push them closer together, it will be first the electrons and then the nuclei that are going to dominate the repulsion. So the third approximation that actually behaves itself at all distances is called the Lennard-Jones approximation. So E of R, and I've got it here somewhere, is E equilibrium to the power 12 divided by r to the 12 minus 2r equilibrium to the 6 divided by r to the 6, which is kind of obscure. So let us think about what this is going to be and how this is going to behave. So I'll draw another plot here. That is r, and that is e. Well, because all the r variables are in the denominator, clearly at infinity this has to go to 0, which is good. As we are coming closer and closer to sort of small but finite values, this r to the 6 is going to be smaller than r to the 12th, and so the whole thing will be negative, and so it behaves like this. Eventually these two terms will become equal and we will go through a minimum, and at very, very small distances r to the 12th is much smaller, and therefore this term much larger than that, and it goes into infinity, and it starts growing considerably earlier than 0, and so it does this. And this is the ELJ, and as you can see, it's actually very much in line with what we would expect from the true interatomic potential. In particular, it tends to work rather well for various inert atoms, where there are no complications related to covalent bonding and so on. If you have argon gas, and you start compressing that gas to a pretty high accuracy, up to actually quite low temperatures, that is a very reasonable interatomic potential for argon gas, and you would predict all of its properties, like heat capacities and so on. So that is actually pretty good. But still doesn't account for all sorts of quantum mechanical effects, like non-Born-Oppenheimer and various localizations and entanglements and polarizabilities and other such things. What is important here is that I've described to you what we call in chemistry an hierarchy of approximations. There is truth, which in this case is quantum mechanics, and the problem for a simple HF system, for example, is just plainly insoluble. Even in 2019, there isn't a supercomputer that will be able to solve hydrogen fluoride honestly using Schrödinger's equation, fully accounting for the dynamics of every particle. It's just plain impossible. It's the biggest system we could realistically handle with honest to goodness Schrödinger is about 4 electrons, and there are more than 4 electrons in HF. And so we must make do somehow, and these are all examples of how chemists make do. They go and measure things experimentally, or they go and compute things for simpler systems, or in this case they just plainly know the answer. We know that it has to go to 0 here. Now we know that it has to go to infinity there, and that it roughly behaves quadratically in between. From vibrational spectroscopy we know that, and so you can sort of draw this anyway from just basic experimentation and philosophy. And then people come and say, well, okay, we can't solve the full Schrödinger, can we win it? And for a long time this quadratic approximation was useful, and it's useful to this day in molecular dynamics, where if you are not sitting terribly far from this minimum, from here to here, which is roughly room temperature, or like your perfect crystal where you're not actually pushing atoms through it, is pretty good. As you will see in vibrational spectroscopy, harmonic approximation gets pretty good. But then chemists come around and say, well, we'd actually like to model bonds actually breaking. And then people say, well, okay, here's Morse, and it models the bonds breaking, at least, to some extent. Non-selectively with errors and so on, but it doesn't. Chemists become slightly happier, but then the nuclear physicists come out and say, well, actually, we'd like to model a nuclear bomb in a supercomputer because we can no longer test it in physical reality. And so we actually love to have, an honest inter-atomic and inter-nuclear potential, and that clearly doesn't work. And then people say, well, okay, here's a better approximation for you called Lennard-Jones, and for many materials, it's actually pretty good. And then if you insist on including quantum mechanical effects like exchange interaction, interaction between the electrons, then there are further approximations. And if you insist on bringing in special relativity, because the inner electrons in uranium, for example, are actually relativistic, they move at a significant fraction of the speed of light, then there are special relativity corrections to that, and if special relativity doesn't cut it, you have to include the antimatter degrees of freedom, and then general relativity, we've yet to get that desperate in quantum chemistry, but the possibility exists. And so this is an hierarchy of approximations. Now, more specifically, and that is the topic of the next lecture, is when you are given a function of x, which might not be computable, or might only be available numerically. And every evaluation of that function could be a week of CPU time on a supercomputer. We would like to have an approximation of the following type. So it will be some constant, then some linear term, then some quadratic term, then some cubic term, and so on. So let's say if it's approximately constant, we stop here. If it's approximately linear, we stop there. If it has a kind of a bend to it, we might add a little bit of the bend. If the bend is serious and complicated, a bit of a cubic polynomial might be added, and so on. This has a name. It's called the Taylor series. And computing the A1, A2, A3, and so on is the subject of the next lecture. And this is how approximations are done in chemistry. There are classes of approximating functions, in that case polynomials. There are approximations with harmonic functions. There are approximations with rational functions. There are approximations with all sorts of orthogonal systems, like wavelets. You must have heard about that in digital signal processing. That do this. So the summary of the lecture, and we will go into building all of this systematically in the next one, is that there are precious few problems in physics that are actually fully solvable, and those have been solved a long time ago. These days, if you have to make progress, you have to treat approximately somehow. This is the philosophy that goes into building and utilization of such approximations. More or less, you just stare at it long enough until you have an idea about how to fudge it. And we will be building systematic fudges next week. Any questions?